Okay, so equivalently, let's imagine that I have a pair of operators and I've got, oh, sorry, let's go there, I'll go there. So I've got a pair of operators, oh, O1 acting on some vector v is equal to lambda 1v, and O2 acting on this vector v is equal to lambda 2v. This is only possible if O1 and O2 are equal to 0. Okay? So if you've got a simultaneous eigenvector of two operators, it's because O1, O2, actually, let me be a little bit more precise. It's only possible if O1, O2 acting on V is equal to 0. That's the only time that you could find some simultaneous eigenvectors. Okay? Now, when we think about P and X, remember what the commutator of P and X is. P and X is equal to minus I H bar. So P and X on any state psi is never 0. And that means because this is never ever 0, what you learn is you can never find a state psi such that P on psi is equal to P psi and X on psi is equal to X psi. So you can never find a state psi that has both a definite position and a definite momentum. Psi does not exist. The idea of that state is wrong. It's mathematically inconsistent. Okay? So why can we never find a simultaneous eigenstate of momentum and position? Why can we never find a state where our particle has a definite momentum and a definite position? It's because of this commutation relation. This is where the uncertainty principle is put into our theory. Inside that uncertainty relation, and in fact, you can use this uncertainty relation to prove, you can use this commutation relation to prove the uncertainty relation. So special relativity tells us that observables must be fields. Quantum mechanics tells us observables must be operators. Okay, I want to develop this idea a little bit more, and I'm going to imagine the following. So imagine we have a particle with spin. So I can measure its spin, and I will get plus or minus a half along some axis. Okay, so I could measure along the z-axis and get plus or minus a half, or I could measure along the x-axis and get plus or minus a half. From your non-relativistic quantum mechanics course, you will probably remember that the z component of spin is given by 1/2 times the z Pauli matrix, and that is 1/2 times by 1, 0, 0, minus 1. So there are two possibilities for the Sz if we measure it. We'll find plus or minus a half. The eigenstate with Sz equal to 1/2 is given by 1, 0. So I hope that's something that you can compute. If not, you've got a little bit of reading to do. And Sz is minus 1/2. That eigenstate is given by 0, 1. Okay. So if you're not familiar with this, please go and look at a good book on non-relativistic quantum mechanics. We could also choose to measure the x component of the spin. The x component of the spin is given by 1/2 times sigma x, also a Pauli matrix, and this is 1/2 times by 0.110. And once again, there are two eigenstates. There's an eigenstate where the x component of the spin is plus 1/2, and this normalized eigenstate is given by 1/√2, 1, 1. And there's also an eigenstate for which the x component of spin is minus 1/2, and this is given by 1/√2, again normalized, 1 minus 1. Why am I choosing to study these two observables? Well, you can very easily calculate using Sz and Sx. So these are operators acting in a two-dimensional Hilbert space. It's very easy to calculate the commutator of these operators and to check that the commutator between Sz and Sx is not equal to 0. And that means that there is no state which has a good value of spin along the z-axis and a good value of spin along the x-axis. We'll continue in a moment.